Okay, here is day 11 polynomial functions. 44 says, let p of x equal x to the fifth minus 10x cubed plus 9x. Find the zeros of the polynomial function by factoring. So we could start by setting this equal to 0, because we're trying to find the zeros. Notice there's a greatest common factor of x, so I can factor that out. And then what's left is a quadratic of x squared. In other words, instead of x squared and x, I have x to the fourth and x squared. So if I could find two numbers that multiply to 9 and add to negative 10, I could factor this. And I can, so that should factor to x squared plus something, and then x squared plus something. That should be negative 9 and negative 1. Okay, certainly x squared times x squared is x to the fourth. I get negative 9x squared, negative 1x squared makes negative 10x squared, and negative 1 times negative 9 is 9. Then continuing, those are two quadratics. Really, I'm looking for two numbers that multiply to negative 1 and add to 0, and multiply to negative 9 and add to 0. But this is also the difference of two squares, which should be x plus 1 times x minus 1, and then x plus 3 times x minus 3. So there you can see fifth degree polynomial, 5 real zeros, x equals negative 3, negative 1, 0, 1, and 3. It says verify your results in part A by graphing the function in your calculator. So y equals, I can put in x to the fifth minus 10x cubed plus 9x. I'll do zoom 6 standard. And these are counting by 1, so that's negative 3, negative 1, 0, 1, and 3. So sure enough, it looks like what I expect it to look like. Looking at 45, given a polynomial function with zeros 1 minus I and 3, find an equation for the polynomial and call it f of x. So remember that if you have a 0 at x equals 1 minus I, you also have to have a 0 at 1 plus I. That's the complex conjugates theorem. And we also have a 0 at x equals 3. So that means we should get x minus 3 as a factor, x minus 1 minus I as a factor, and x minus 1 plus I as a factor. I'm just subtracting these two and distributing the negative. If I multiply these out, I should get x minus 3 times, okay, so I'm just going to distribute this to be careful. I should get x squared minus x plus ix minus x plus 1 minus I minus ix plus I minus I squared. And that's x minus 3 times x squared. The ix and the negative ix are gone. The negative I and the I are gone. This is negative 2x. And then I have a 1 and a minus I squared. But remember that minus I squared is negative 1, so this should be plus 1, so it should be plus 2. And then distributing again, I should get x cubed minus 2x squared plus 2x minus 3x squared plus 6x minus 6, which simplifies to x cubed minus 5x squared plus 8x minus 6. So this would be f of x. Of course, it's possible that there's some leading coefficient, but it just says find an equation for the polynomial. So this is definitely 1. How many x-intercepts does the polynomial f of x have? Well, it has 1 x-intercept, because it has two complex roots. So if we were going to verify in the calculator, we could simply graph x cubed minus 5x squared plus 8x minus 6. And we will get a graph that looks like this. And there's my 0 at x equals 3. (46) says, suppose h is a polynomial with real coefficients and h of 7 minus 3i equals 0. So if this is basically saying that this is a root of h, well then its complex conjugate also has to be a root. So that also has to equal 0. That's the complex conjugate theorem. (47) says, consider this 4th degree polynomial. Verify that I is a 0 of f of x. To verify, we need to just plug it in. So that would be I to the 4th minus 4i cubed plus 30i squared minus 4i plus 29. So I to the 4th we know is 1. I cubed we know is negative I. So this is going to be plus 4i. 30i squared is negative 30. And I have negative 4i and plus 29. Negative 4i and 4i are gone. 1 minus 30 is negative 29. Plus 29 is 0. So I is in fact a 0 of this polynomial, because when we plug it in we get 0. It says via log division and the factors you found in part A, notice I said factors, find the remaining zeros of f of x. Okay, so what we know is I is a 0, and thus negative I is also a 0. Right? Those are the complex conjugates. So we should have x minus I and x plus I as factors. If we multiply those, we get x squared minus ix plus ix minus I squared, which is simply x squared plus 1. So x squared plus 1 is the quadratic that has roots I and negative I. So now what we can do is divide our polynomial by x squared plus 1 to see what's left. So x squared plus 1 goes into x to the 4th minus 4x cubed plus 30x squared minus 4x plus 29. It goes in x squared times x squared is x to the 4th plus x plus 0x cubed plus x squared. I probably need a 0x in here to help me remember. If I subtract, I get negative 4x cubed plus 29x squared minus 4x plus 24. So now I should have minus 4x. Gives me negative 4x cubed plus 0x squared minus 4x. And that should give me negative 29x squared. This is a 29. Plus 0x plus 29. And now it should be minus 29. And I get negative 29x squared. So no, this should be positive 29. And this should be positive, because I'm not subtracting the 29, I'm just subtracting 0 from 29. So I should get 29x squared plus 29. And when I subtract those, I get 0. That makes sense, because we already know that this should be a factor of that polynomial, so my remainder needs to be 0. So now I know I've got x squared plus 1 times x squared minus 4x plus 29. That's my 4th degree. It says to apply the quadratic formula to this because perhaps it doesn't factor. So I know the roots of that are going to be x equals negative b, that's 4, plus or minus the square root of b squared, 16, minus 4 times a times c, all divided by 2a. So that's x equals 4 divided by 2 is 2, plus or minus the square root of, so let's see here, 4 times 29 is 116, so this is 16 minus 116, or negative 100 divided by 2. So x equals 2, plus or minus square root of negative 100 is 10i divided by 2, so x equals 2 plus or minus 5i. So The remaining zeros of f of x are 2 plus 5i and 2 minus 5i. So we can see that this fourth degree polynomial has 4 complex zeros. Says for 48, says what are the zeros of 5x minus x cubed? Well, 0 equals 5x minus x cubed, so 0 equals x times 5 minus x squared. So 0 equals x, or 0 equals 5 minus x squared. So this would be 5 equals x squared, or square root 5 equals absolute x. So root 5 equals x, or negative root 5 equals x. So x equals 0, and x equals plus or minus square root of 5. Okay, 49 gives us a graph. It says its 7th degree increases without bound, meaning it is increasing over here. What are the zeros of g of x? State each zero's multiplicity. Here's a 0 at negative 5 with multiplicity 2 because it bounces off the axis. Here's x equals negative 1 with multiplicity 1 because it goes straight through. Here's x equals 4 with multiplicity 3 because it bends as it crosses through. And here's x equals 7 with multiplicity 1 because it goes straight through. So hopefully those multiplicities add up to 7. 1, 2, 3, 6, 7. Yes, they do. So that makes sense. I've got 1, 2, 3, 4, 5, 6, 7 factors, and that's giving me a 7th degree polynomial. It says the y-intercept of g of x is this. Find the equation. Okay, so let's write out the factors. I should get y equals a, some leading coefficient, times x plus 5 times x plus 1. This x plus 5 needs to be squared because of the multiplicity 2, times x minus 4 cubed because that has multiplicity 3, and x minus 7. So there's again 1, 2, 3, 4, 5, 6, 7 is my degree. Now, if I want to find the y-intercept, I can plug this point in. So 1, 1, 200, excuse me, not find the y-intercept, but find the leading coefficient to make the y-intercept match. That equals a times, now I'm plugging in 0 for x. So 5 squared times 1 times negative 4 cubed times negative 7. So 1, 1, 200 equals a times, so finding all this, I should get 64 times 25 times 7, which is actually 1, 1, 200. So that means that 1 equals a. So it actually works out perfectly in some ways. And so I can just have y equals x plus 5 squared times x plus 1 times x minus 4 cubed times x minus 7. And I'm not going to bother multiplying that out because it doesn't ask for it in standard form. It says on which intervals is g of x greater than or equal to 0? Well, it's greater than or equal to 0 at x equals negative 5 because it's equal to 0 there. It's also greater than or equal to 0 for negative 1 is less than or equal to x is less than or equal to 4. And for x is greater than or equal to 7. I could also write negative 5, negative 1 to 4, and 7 to infinity. That's when g of x is greater than or equal to 0. On approximately which intervals is g of x increasing? Well, it looks like it is increasing from negative infinity to negative 5. Then it increases again from negative 3 to approximately 0.5. Then it increases again from approximately